Here is a technical result by Carathéodory, which will prove fairly useful when we try to prove other results. Let's say you have a function f from an interval I to the reals and some point c in the interval. F is differentiable at the point c if and only if there is a function phi also from I to r with the following properties. It is continuous at c, and the difference between f at x and f at c is obtained by multiplying phi at x times x minus c for every x in your interval I. And if that's the case, well then the derivative of f is actually just phi. Now what's important is the derivative at c, not the derivative everywhere over the interval. Well, let's prove the first direction. Let's assume that f is differentiable at c. So if f prime at c exists, we'll define our function phi as follows. It is either going to be the differential quotient f at x minus f at c divided by x minus c, when x is an I and x is not equal to c, so we can actually divide by x minus c. Otherwise, because we do know that the function f is differentiable so that f prime at c exists, it'll be f prime at c when x is equal to c. Now, let's compute the limit when x goes to c of phi at x. Well, when we compute the limit, x is in general not equal to c, right? And so we find ourselves in the first branch of the function. This would be the limit when x goes to c of the differential quotient, which by differentiability of the function f is exactly the derivative of f at c. And by construction, this is exactly phi at c. So what this means is that phi is continuous at c. If x is equal to c, let me look at the construction f at x minus f at c. That would literally be f at c minus f at c, which we know to be 0. On the other hand, phi at x times x minus c would be equal to phi at c times c minus c, which is also 0. So if x is equal to c, then f at x minus f at c is equal to phi at x times x minus c, the special value x equal to c. If on the other hand x is not equal to c, then by construction f at x minus f at c is exactly equal to phi at x times x minus c. Just take this chunk here. In both cases, f at x minus f at c equal to phi at x times x minus c. We've proved the first direction. Now what about the other direction? So we assume that there is a function phi from I to r continuous at c such that fx minus f at c is equal to phi at x times x minus c for every x in I. Then, if x is not equal to c, we can rewrite the expression here as follows. But it turns out that by continuity of the function phi at c, we can also write phi at c as the limit when x goes to c. Phi at x, when we compute the limit, x is not equal to c, so we find ourselves in this situation. This is the limit when x goes to c of the differential quotient. Phi at c exists because the function phi is actually defined on the interval I, and c is in the interval, which means that this limit exists. And that means that f is differentiable. We can say a bit more than this. Because the limit exists and f is differentiable, this is exactly the value of phi at c. And that proves a theorem. How is this theorem useful? Well, we can use it to prove the chain rule, which is basically the building block of differential calculus. Here we have I and j intervals. We have a function g from I to r and a function f from j to r. Let's assume further that the image of j by f is contained in the interval I, and that C is in the interval J. If f is differentiable at C, and if G is differentiable at f at C, which is the image of C by f in the interval I, hence in the domain of G, then the composition of G and f is differentiable at C, and the derivative of the function at C is given by the chain rule, which you remember from calculus. Let's see the proof of this result. The function f is differentiable at C, so f prime at C exists. It's well defined. And then we can use Carathéodory's theorem to show that there exists a function phi from the same domain as f, such that it is continuous at C, and the following expression holds. Now similarly, because the function g is differentiable at f at C, again you can use Carathéodory's theorem to find the existence of a function psi, this time from I to R, such that psi is continuous at f at C, which we will call d, and the following expression holds. G at y minus g at d would be equal to psi y times y minus d. Of course, here we can change the name of the variables without too much of a hassle, right? This is the same result. Now, this is true in the first case for every x in the interval J, and in the second case for every y in the interval I. In particular, we also have that phi at C would be equal to f prime at C, and psi at D would be equal to g prime at D. That's part of Carathéodory's statement. If we let y stand for f at x, and d specifically f at c, as we had originally denoted it, then you can write composition of g with f at x minus the composition of g with f at c is going to be equal to, well, first of all, that's just g at f at x minus g at f at c, which if you want, you can think of as g at y minus g at d. That's going to be equal to psi at f at x times f at x minus f at c. Why? Because by Carathéodory's theorem, g at y minus g at d would be equal to psi at y times y minus c, and y is f at x and d is f at c. Well, that's equal to psi at f at x for sure, and now f at x minus f at c by the first part we saw on the previous slide. This is going to be equal to phi at x times x minus c. So I can do a little bit of rewriting. This is going to be psi composed with f at x times phi at x times x minus c. This is true for every x in the interval J, assuming that f at x is an I. As we saw in the previous slide, the function psi composed with f is continuous at x equals c, and we know that because psi is continuous at f at c, which was d. Similarly, we know that phi is continuous at x equals c by Carathéodory's theorem in the first place, and so the product of psi composed with f and phi is continuous at x equals c. Now look what we've written here. G composed with f at x minus g composed with f at c is equal to some function at x times x minus c for every x in the interval J. By Carathéodory's theorem, what this says is that the derivative of g composed with f at c is exactly this expression here at c. But psi composed with f at c times phi at c, that is what this expression here is, simply psi at f at c times phi at c. And again, by Carathéodory's theorem, phi at c, that's f prime at c, and psi at f at c, that's g prime f at c. And so we have the chain rule. The derivative of g composed with f at c is g prime at f at c times f prime at c. And what are some consequences of that chain rule? Look, let's say you have a function f from I to r, differentiable on the full interval, so at every point c in the interval, and assume that neither f nor its derivative are equal to 0 over the interval. Consider the function h, which to every y associates 1 over y, assuming of course that y is not 0. If we assume for now that we buy into the power rule for the derivative, and all we're really missing here, thanks to a result from the previous video, is the derivative of the identity function, which we'll work on later, then the function 1 over y, assuming y is not equal to 0, has the derivative minus 1 over y squared. The consequence of this is that if you consider the function 1 over f, and you look for its derivative, well, you first rewrite 1 over f as a composition of h with f, and by the chain rule this would be h prime f at x times f prime at x, and we know what h prime at f at x is. This minus 1 over the square of f at x from this one, so that the derivative of 1 over f is really minus f prime at x divided by the square of f at x for every x in the interval. Another example, say we have a function g defined by the absolute value. Then the derivative of g is a signum function as long as x is not equal to 0. What happens at 0? Well, g prime cannot be defined. We'll see why. And what happens at 0? Well, the signum function is defined at 0, right? We know that signum of 0 is 0, but g prime at 0 is not defined. If f is some differentiable function over the interval I, the chain rule tells us that the derivative of the absolute value of f would be the signum of f at x times f prime at x. And that's going to be f prime at x if f at x is greater than 0, or minus f prime at x if f at x is smaller than 0. But what happens if f at c is equal to 0? What's the derivative of the absolute value of f then? Is the function absolute value of f even differentiable at